Devashish Kumar. I have a bachelor's and master's degree in civil and environmental engineering. And then I worked as a risk engineer at Data Risk for about 3 years. I was primarily doing assessment of buildings, evaluating structural integrity of buildings subjected to main hazards such as fire, cloud explosions. There I was primarily doing a component level analysis. I would look into, I will take a building, I will look into different components of the building separately, roofs, columns, walls, doors, windows, versus the structural integrity of the building. And then I worked as a risk analyst for about 2 years at Swiss Re. Here I was looking at a portfolio of buildings, not 1, 2 or 10 buildings, but sometimes even 1 million buildings together, a system level analysis. And this was in 2010 when I joined Swiss Re. Industry was still recovering from, I'm talking about Hurricane Katrina. Katrina was the major attention, major focus, but if you remember, there was a series of hurricanes just happened before Katrina and after Katrina, such as Hurricane Charlie, Wilma, Francis, Ivan, and then in this area we had Irene in 2011. And when I joined in 2010, there was a series of earthquakes just within a span of 1 year, starting from Chile to earthquake in New Zealand and then even in Japan. And then we had another big event in Thailand flood. So there was a consensus building in the industry that somehow they are seeing huge increase in losses coming from natural catastrophe, mostly from weather extremes, mostly from related to hurricanes and floods. And they were attributing these regions, 4 regions they were attributing it to. The 3 regions were changing, increase in exposure on the coastal regions. People are moving more to the coast, so basically moving in the more vulnerable areas. And then there was increase of insurance penetration. As economy grew, more and more people were buying insurance. And also the property values were increasing. In last 10 decades, the value of houses has increased significantly. Somehow these 3 factors were already taken care in this model. If not, they knew how to tackle it. But the other 4th reason they had started attributing it was climate change and climate variability. They were still feeling this could be the reason for the recent increase in the number of hurricanes and their intensity, but they were not exactly attributing the reason as climate change. So this was in 2010-2011. When I joined Northeastern in 2012 as a PhD student, at that time I thought I will do my research on climate change and variability, and I will look at the impact on critical infrastructure and key resources. This way I can bring my 5 years of prior industry experience of risk analysis, and then I will learn something and do something in climate change, and I will integrate this together. So when I had just joined here in the first semester, I started putting up an overview framework for my whole PhD. The idea was to summarize my prior experience, and then what I will do in my PhD, just keep building on this framework as I go along the PhD path. So when I started, these were the skills that I brought here. I also learned here when doing my PhD program, but I had idea about exposure vulnerability, how to define and hazards, how to do risk assessment, and then how to quantify insurance losses. And then I added the remaining components here over the period of 4 years where I brought climate as a stressor. Earlier, there are insurance companies which do not even use this regular NatCat models for pricing, such as Lloyd's of London, but now even they think climate is a game changer. Earlier they were not even believing in them. So I added these components for the climate and sources, and this is the whole overall overview looks for my PhD program, and this whole framework had guided me in my whole research. As it is evident from my research publications, I have tried to touch on almost everything that I have listed on here, 1 or 2 components which I have not touched on during my PhD program. So this framework has been a very, very great guide to me, in guiding my research. So when I had just come here in 2012, which outputs from the latest generations of global climate models had just started coming, and these global climate models were collectively called CMI5. CMI stands for Coupled Model Intercomparison Project. So the first research topic I was working on how these models are performing, in simulating signal and regional mean climatology, how these models are performing compared to the previous generations. And the basis of this hypothesis or research questions were that the This previous generations of climate model CMIP 3, which was the IPCC fourth assessment report, which came in 2007, was based on CMIP 3. So CMIP 3 had performed much better compared to the previous generations of CMIP models, CMIP 1 and CMIP 2. So this was a study published in BAMS in 2008, where they compared the three generations of global climate models with respect to some metric, and they showed the consistent improvement in subsequent CMIP generations. What this metric is showing is that with some calculations, they calculate this metric, and then the idea is that if the value is coming less than 1, the models are performing better, they are more accurate models. If the value is further from 1, then these models are underperforming. In the first generation, in the first row that you see, most of these models are lying on the right of this vertical line, which represents 1. In the second generation, some of the models are shifting towards left. In the third generation, most of the models there at left of this vertical line, a few models were also on the right. But they were consistent in increasing the model performance. And to the point, this the fourth assessment report, which was basis for CMIP 3, got Nobel Peace Prize in 2007. And based on this performance, there were also some issues that were identified at that time, and they were the consensus that these issues will be addressed in the next generations of climate models. And this is the new generation, which is called CMIP 5. So one question that the research question that I had at that time, see how these CMIP 5 models are performing compared to the previous generations, and how these models themselves are performing in similar historical climatology. So these were some of the improvements were implemented in CMIP 5 models. There were many models with increasing spatial resolution. There were models which had carbon cycles, and they are now called Earth system models. There were models which had dynamic land vegetations. Not all models had all of these features, but there were models which had these features. Again, to hope that these models will do much better than CMIP 3. And just to give you an idea, CMIP 5 is a massive effort of 5 to 7 years of work. Lots of coordination among the modeling group had happened, and lots of time had taken to run these experiments. And just to give you another idea about the massiveness of the CMIP 5 is that CMIP 3, the whole data set was just 36 terabytes. In CMIP 5, the data set spans around almost 3 petabytes. So it was a massive task with lots of hope. Some of the research questions that I was asking at that time, how these models are performing in simulating the historical scale and compared to the previous generation? Has the multimodal variability reduced in these models? When I see simulating historical scale, multimodal variability is one measure of uncertainty coming from these models. If this has reduced, then we understand more about these models. Our understanding has improved, and not only improved, we have implemented something in much better way in these models. And then how the model consensus has increased as the model consensus increasing projecting future climate change. In future, we don't have observations, so we rely on that the more and more models agree on the same thing, and we think our understanding is better. And then in CMIP 5, we have a new sets of greenhouse gas emission scenarios. There was a different sets in CMIP 3, so the idea is how the climate change will look under the new greenhouse gas emission scenario. So with these 4 questions, I collected data from these 11 climate models. When I started doing this work, data from not all models were available. And also the number of models in CMIP 3 was around 20, number of models in CMIP 5 was around 40. But idea was to do one-to-one comparison. So my maximum model I had to select by 20, but then also in CMIP 3, some of the models had very poor grid resolutions. And to compute some of the metric, I have to interpolate those data. Interpolations introduce another additional inaccuracies. So I just zeroed down on 11 pairs of climate models from both generations. And then I did the study for the whole globe. So as a reference data set, I considered 2 sets of reanalysis data and 1 set of observation data. And step 1 and then step 2 was the reanalysis, and GPCP for precipitation was the observed data. I considered both temperature and precipitation, and I focused on 2 seasons, summer and winter. Again, my focus was not so much on the whole world, but more on the regional scale, because one of the purpose of running these massive experiments in CMIP 5 was to do much better job in projecting regional climate change. Because if you want to adapt, you adapt locally or regionally. You don't adapt for the whole world. So I wanted to evaluate the performance of these models at the regional scale. And I divided the whole world into 22 regions based on some classifications that existed in the literature. And then The selection of model diagnostics and performance metric I did, I wanted to cover all aspects. It was a very comprehensive analysis at that time. So I considered 4 metrics. The first one was a spatial map showing model biases. Where do we see model is underestimating or overestimating the climate change compared to the reference data set. So this gives me an idea about the mean climate change and a spatial variability. And then I looked at time series of the climate change. This gives me an idea about temporal variability and also the multi-model bound, once some kinds of the measure about uncertainty. And then I looked at Taylor diagrams. Taylor diagram essentially captures 4 statistics about these model performance like a standard deviations and cross correlation coefficients between them and summarizes them into a single metric. And then I also looked at the some kinds of a skill score based on the probability distribution function. The idea was that simulating a PDF is much harder test than capturing the first or second moment in mean on a standard deviation. So the paper was published in Climate Dynamics in 2014, and I have done a very comprehensive analysis. So there are lots of results in this paper, but just for the sake of the presentations, I'm showing only few results to make the conclusions, to convey the conclusion. So here I am showing summer rainfall time series over 3 spatial regions. Just to, let me give you the idea about this plot. So here I am showing the mean median times with multimodal median rainfall. In blue and red color is the CME 3 and CME 5. And then the black solid line and the dotted solid line is one of the reanalysis data sets. And then the green line is the GPCP, the observational rainfall data set. And the shade is showing the multi-model bond, basically coming from 11 models, the minimum and the maximum. So if you look at for global land, the multi-model median is contained within the bond, which is obvious, but then also the variability coming from CME 3 and CME 5 for the mean rainfall pattern change is almost following the observed or reanalysis data sets. And also this observed mean rainfall pattern is contained within the multi-model bond. So not much difference here in performance. This looks very good. But when we go for the southern Australia or say Amazon basin, what we see here is that the multimodal median rainfall either coming from CME 3 and CME 5 is overestimating the observed rainfall. In the case of Amazon basin, it is underestimating the observed rainfall. In the case of Amazon basin, it is underestimating the rainfall. And also, if you look at the observed variability coming from the reanalysis or observation data set, sometimes they are exceeding the bounds of the multimodal. So, with many other figures that I have in the original paper, the conclusion I came about that CME 5 models are not necessarily showing improvements compared to the previous generation in simulating seasonal climatology at regional scale. Also, the multimodal median variability is almost sometimes they don't even match the observed variability. So, all the massive effort that gone into building these new generations of models for 5 or 7 years was not necessarily giving us any better model than what we had earlier. However, the components that they have added in these new generations of models will help in future development of these models. Some of the carbon cycle feedback, some of the other processes which were missing in the CME 3, they have been added, but somehow with the time constraint, those additions were more of an ad hoc basis, so the performance did not show up in this generation. In CME 6, the next generation they are planning, the performance might show up. So, and after this evaluation of CME 5 models for the mean climatology, I started working on wind extreme. The motivation for this research came from twofold. One, our MathCode had a proposal displaced where they wanted to look at winds and over 30 years from now to 30 years. And then when I was doing literature, I did not find many papers on wind extremes, and in our lab we were already working on temperature extremes and precipitation extremes. This was one area which was not touched that much. So, and when I was working in the insurance company, they were saying the losses coming from the hurricane is increasing, and one of the prime driver of the hurricane losses is the wind, other is the surge. So I wanted to look at how these models simulate extreme winds and how the future extreme wind, how the extreme winds will look to the future. There was another paper in Nature Geoscience, very high impact journal, where they reported that the extreme winds are declining over United States and over many regions over northern hemisphere tropics. So, but we see that the losses from the insurance companies are increasing because of the stream wind. So there is a conflicting or contrasting reporting here. So the research question here I defined was that how the CH5 models are performing in simulating with the stream winds and how these stream winds will look into the future. And when I did the literature review, I found that CH5 models, some of the CH5 models had been specifically designed to address the wind patterns. Like in CMIC 3 models, they did not had models which would simulate wind at a very high pressure level. In CMIC 5 model, they added more pressure level. So essentially, this CMIC 5 model should perform much better in simulating extreme winds. Again, this was a little lengthy paper, and the paper was published in Climate Dynamics. So I obtained the daily mean wind speed data from 15 climate models. Not all climate models give this wind data, and for the reference data set, I took the third generation of reanalysis product ERA and pairing. And in the first set of analysis, what I did, I looked at the multi-model median bias from these 15 models. And when you look at here, this is the reference, this is the reanalysis mean for annual maximum wind speed. What we see here is that the biases, when I look at the bias map, the light shades of orange and blue show me very less bias, but the deeper shades of red and deep show a strong positive or negative bias. If you look at this map, all over the world, you have not much strong bias except over Himalayas, Siberia, or this Rocky Mountain, and also along the Andes. So, what these models are doing is that they are simulating the mean of or the annual maximum wind speed reasonably well except over the mountainous terrain, which is not so. It is obvious because these models are not dissolve this complex topography that well. And I also did this trend analysis of the extreme winds. The reason being that there was a report in Nature Geoscience that the extreme winds are declining. So this is the here I'm plotting the slope of this slope of wind speed, extreme wind speed, and this is coming from the reanalysis data sets, and this is coming from the multi-model median, 15 models. If you look at here, there are many regions, especially over years when they said the wind speed is declining. This reanalysis data sets do capture because this minus speed shows the declining wind speed, and similarly many other regions over northern hemisphere, the blue shows the wind speed is declining. But when I look at these models, over US, yeah, the wind speed is declining, but the intensity of the wind speed declining is not as much as the observation says. Similarly, there are many other points, there are many other regions where the wind speed is not either declining or increasing at that pace that the reanalysis of the observation says. That essentially means that this multi-model median is not capturing the trend in the wind speed. When I was saying here, they are capturing the mean of the extreme winds, but the trend is not getting captured that well, especially over some regions they do have high wind speed. And then another interesting statistic that I wanted to look at is the extreme winds, because to design of buildings, especially in hurricane-prone regions and wind turbines, requires estimates of quantiles of wind speed that can happen once in 50 or 100 years. So these statistics that I showed you, I did with the annual maximum wind speed. But here, for design of buildings, another wind turbines, you need to estimate quantiles of wind speed that can happen once in 100 or 50 years. So one of the common conventions that as a hydrologist and climate scientist follow when we do estimates of when we have to estimate quantiles of extremes is that we should generalize extreme value distribution and we estimate the quantiles from there. However, when I did some literature review from wind engineers, where the wind engineers published the research and the structural engineers published the research, they completely said we should not use GEV, we should use only Gumbel distribution to estimate quantiles of wind speed. And this was not very familiar in the climate literature because I saw papers where people were still using GEV to estimate quantiles of wind speed. However, one researcher, Sarah Pryor, she is the leading scientist when it comes to wind and climatology from climate side. She has also advocated the use of Gumbel distribution. She doesn't recommend using GEV. This was a new learning for me at that time. The reasoning they say why we should use Gumbel distribution is coming from twofold. One of the theoretical consideration is that the velocities follow Rayleigh distribution, And this distribution is nothing but a special case of a Debye distribution, and Debye distribution is a exponential distribution. So in the asymptotic limit, that any exponential distribution follows Gumbel distribution. So this is a very theoretical reason that this literature cites. And then from the practical consideration comes from this analogy that generalized stream value distribution is nothing but it has a combination of three distributions, and Gumbel is one of the distribution. So, and these three distributions are connected through the shape parameter. So let the data decide, let the data say the shape parameter will be 0 and then it's a Gumbel. But what happens with the small sample size, even when you do the estimation, shape parameter may be close to 0, but it's never exactly 0. It's either a small value of negative or small value of positive. So it usually picks up the other distribution, but not the Gumbel distribution. And when they do significance test, they find that the significance test is always failing there. And also, when they plot this data on probability plot paper, they see that there is no genuine examples of either type 2 or type 3 distributions that you have in GED. So these were the theoretical and other considerations for using of the Gumbel distribution. So I got the data for the future wind speed from RCPX and site scenario. This is one of the future scenario for the greenhouse gas emission. And computed the quantiles of 100-year wind speed and compared with the historical and the future. Again, these are the means from 15 models. And what I see is this statistics I'm showing towards the end of the century, from 2074 to 2100. So what I see here is that over certain regions, especially in tropics, there will be places where wind speed would be increasing, not huge, but definitely by 1 to 2 meters per second. And these are the regions, Amazonia, over India, and then some regions in Africa. But if you look at the absolute values over these regions, we don't have the maximum wind speed to start with, but these regions will experience more and more extreme in the future. So next, what it comes, when I was working on my wind extreme paper, there was a proposal request that came from ARPA-E, the research arm of Department of Energy, where they wanted us to look at how much power production will be at risk over US at near term. When I say near term, from now to 20 to 30 years. They were interested in for a couple of reasons, but one of the things that we kept telling them, when we look at data from climate model, they wanted to look from the two stressors they wanted us to study. One was the availability of fresh water, scarcity of fresh water in the future, and also increase of population, so sub demand side. We will have more demand of water. One of the things that we told them in the beginning when we were defining the problem for writing the proposal, that from the climate model, we usually don't look for the 10 or 20 or 30 years. We usually look for the mid-century or end century. And other problem constraint, but they were very fixed that we want to look something over the near future. Another constraint that they had is that they wanted to look over a 5-year averaging period, but multiple 5-year averaging period, so that they could guess the risk profile, how it is changing with time. And again, we in climate, we at least take 10 years of average to do climatology, because natural fluctuations otherwise does not get smoothed out, and the climate trend is not coming out that well. So this was two challenges. They were interested in 0 to 30 years and also 5-year averaging, which was very, very unconventional for a climate guy to do that. But still, to fit the requirements, we did that, and then we started. Once we had the proposal, then we started working on the problem. Then one of the first thing we did was that learn about how the uncertainty in climate projections, what is their role and how they dominate. So the uncertainty in climate projections comes from three different sources. One is called internal variability, second is model spread, and third is scenario uncertainty. Just to give you a schematic picture of what I mean by that, here this picture is taken from IPCC report, the latest report that came in 2013. Here I'm showing a time series of temperature increase at the global level, global scale. This black and gray shades is showing the observational record, and the color is showing the coming from the model. So you see three color scheme here: orange, blue, and green. The orange one is one which is coming because of the internal variability. What it says that even if you have the even if you run the same model with same forcings, but if you slightly change the initial conditions, that is equal to 0 parameter, the future will evolve differently after certain time because of the chaotic interactions that happen between the components of systems. And then the blue line is showing the result, the uncertainty because of the coming from different models. What it means, two models give you different future, even everything remains the same in those. The reason because these models are built differently and they require lots of parameters, and these different models are using different parameters. And then the third one is green line is called scenario uncertainty. We don't know how much emissions will be in the future, both anthropogenic we don't know, and how much also the natural causes. So uncertainty because of that is captured by the green line. So these are the three major sources of uncertainty. Here the interesting part is if I just take the relative contribution of the uncertainty, a simple measure is if the width of the band gives me that the uncertainty measure, then if you look at as you move from now to 2100, the relative contributions of different sources of uncertainty is changing. The orange line is dominating in near future, and as you move further, the blue line is dominating, and then at the end of the century, the green line is dominating. So if I have to do any impact assessment from now to 30 years, for me the major sources of uncertainty is coming either from internal variability or from multimodal spread. Basically, because of the chaotic interactions or because what we don't understand what the climate physics and how we have included in the model. So this is at the global scale. What we want to do for the whole US is a continental scale, because at the global scale, averaging a smooth source, many of the other sources of a smooth or the uncertainty. So when I look at the Europe, because for US the IPCC did not do that analysis. For Europe, if you look at this is the same picture here as a magnified, much more magnified way. The orange band or the internal variability is very dominating factor until from now till 2030. So one of the major practice has been in climate impact assessment to consider data from multiple models, but not necessarily consider data from multiple initial conditions or to capture internal variability. But if we have to do any analysis that will focus from now to 30 years or 20 years, we have to include in internal variability. This is the message coming from this picture. And the way this figure has been generated, they have to make lots of assumptions. The assumptions was that they had to estimate the climate trend. To estimate the climate trend, they assumed a fourth-order polynomial. Basically, they took one climate model output, they fitted a fourth-order polynomial, and whatever the residual was left, they called them as the internal variability. But in a regression, the residuals are always a stochastic variability. It's not internal variability coming from a deterministic system that is chaotic. So these two assumptions I had to make, and if you look at this, the smooth line that you see, the boundary between the two sources of uncertainty is very smooth. In real life or in real climate model, will never ever give unless until you make these assumptions. So, but this acted as a guide for us, and then from here, what we did is this was a motivation, further motivation for me to define my next research problem. So I looked at rain followability over US in 2030 compared to now. I took data from 3 climate models. I computed fresh water availability. Very simple measure, whatever rainfall is coming on the earth and whatever is getting evaporated, T minus E. And if you look at these three, the first row, the first 3 columns, this is US Department of Energy model. It says that the US will be wet. This is NASA model again coming from US. This says the US will be dry. And this region of US will be wet, but then this model says this region of US will be dry. So you see very complete different opposite patterns here. This is one of the Japanese models, which is one of the good models in CNE 5. This has almost saying US will be dry, but also will be wet. So this model, this line is showing we have lots of multimodal variability when we look at fresh water availability over US. And we are aware of this. That's why we take multimodal. We don't take one model to do any impact assessment. And this is the multimodal mean. What we did next, so this was the analysis, this was the data taken from the first initial condition from the CNE 5 or 5. We took another initial condition run. And when I look at here, if you look at from the same model, this is very different world altogether. Here US was wet, here US is dry, and the reason it was wet, this is here, this is wet. This reason it was dry, this is wet. So completely different. And so far, if we are not considering the impact of if we are not considering internal variability in our account, then we would be ignoring these climate futures. But these are all very possible future trajectories. These are all plausible futures. And this is coming from the NASA model. This is again very different picture. Here it was dry, but this is getting wet here. And this is a third model. And this is again mean. These 6 scenarios that I am showing, each of them represents one possible future for the possible future climate. We don't know which one is true. So in true essence, we should be considering all 6. And actually, why only consider all 6? We should be considering many more models and many more initial conditions. But for under semi-fiber type, we do not have data available from more than 2 or 3 initial conditions. Only 1 or 2 climate model gives. So for this analysis, this was just a preliminary analysis. We restricted to this 6 future, where we took 3 climate models and 2 initial conditions, and did the analysis for our the work was published in a Science journal. And this is showing the mean of the initial conditions, and this box here shows the mean of all 6. So if you just consider the mean of all 6, this again does not give you the right picture for the extreme cases where you want to consider the water scarcity to look at the power production at risk. So this motivates me further to study more about the internal variability and model response variability in a much more structured and systematic manner, which was not done in the case of IPCC because of the data availability at that time. So just to highlight one more time the importance of internal variability. Why this problem becomes more challenging when we do a weather prediction problem. The weather prediction problem is an initial value problem where we observe the climate state and run the models and then predict the weather for tomorrow or 1 week after now. For the climate problem, which is mostly focused towards the end of the century, we don't care about these initial conditions that much. We care about the climate trend. So the initial information that we know about the today's climate gets lost there anyway. But when we talk about the from now to decade or 1 decade or 2 decades, where this intersection comes, the initial value problem and the boundary value problem. So this is a very gray area right now. People are trying to do something here, but again, we do not have much understanding how to proceed that forward. And this box highlights for me why climate internal variability is important, because it is important over near term 0 to 30 years. It is important especially at regional scales, even at a continental scales. It is important for extremes. It is important for hydrological problems, and all of these are important for multiple stakeholders. So for us, Massford was interested in from now to 30 years. R5 was interested in now to 30 years, and recently we saw a proposal coming from Department of Defense. They are interested in 2 to 20 years. So more and more stakeholders and decision makers are interested in looking at climate as a stressor from now to 20 to 30 years, and at that scale, climate internal variability, this orange line is very important. Multimodal blue variability is equally important, but we have already acknowledged that this is important. So with this background, I had defined my next research problem. Just to add to one more important thing here, one paper came in Nature in 2013. This paper gave an estimate for the year in which the climate signal will emerge from the background noise of the variability. What it means, if you plot the temperature record, you will see it's going up and down, but there is a bond. And when you merge this observed temperature record with the model runs, you will see in the future some year that these model runs will never come into that bond. It will always have the historical bond. So they say that is the year of emergence of climate signal, and that is very important for adaptation, because we know that after that we will not have a temperature record that has ever been observed. But one of the fundamental assumptions or ignorance that did in their estimation was they did not consider internal variability in their calculations or estimates. And a paper followed in Nature under the title called Brief Communications Arising. Nature rarely published a rebuttal article of their own, but this time they allowed. And this came in again 2013 by many leading climate scientists, where they showed what are the fundamental flaws in this paper. And some of the assumptions they highlighted. One of the bigger assumptions was they did not consider internal variability. So again and again, I want to highlight the importance of internal variability in climate impact assessment problem, where the interest is at a regional scale, and near term. So with this background, I defined my research problem, and then the way I designed my experiments is the reason why people were not considering internal variability that much, because we don't have data that much. Last summer, however, one group at NCAR, they ran temperature simulations with only one climate model. There are 30 different initial conditions runs. So this was last summer, because there was growing sometimes Clara Desser, who led the effort, she attended the conference, and there people were saying that if we If we invest more in these computer climate models, then there would be time they will reduce the uncertainty to the point they will believe in this climate change signal. What she wanted to point out that there are some sources of uncertainty which we will never be able to reduce. Doesn't matter how much we invest in these climate models, and that was the internal variability. To highlight that point, she ran simulations with 30 different initial conditions with only one climate model, and then from semi 5 sets we have about 40 models run using few initial conditions, but I took the first initial condition and I thought I will do a direct comparison. I don't have to here indirectly estimate the internal variability by making assumptions about fitting a regression line and then checking the residuals as internal variability. And some other literature that I did search in the previous decade, they were doing even basic estimates of internal variability, so they were not able to characterize the internal variability that it should be. So the problem I did highlight performance sensitivity analysis, where I will compare 30 initial conditions with one model and 30 model runs with one initial condition. And the first thing I did, I defined a metric of relative agreement. How these 30 different models and how these 30 different initial conditions agree with each other. So this was a metric. This is dimensionless, and the value runs between 0 and 1. This was a metric already defined by IPCC in their last assessment report, but they discontinued this metric in the newer report. The way this metric, the value is that if you have is value equal to 1, then you have perfect agreement. Basically, 30 people agreeing on the same thing, there is no disagreement, so you have less variability. And then if the value is 0, then nobody is agreeing on anything, then you have more variability. This is how the simple interpretation of this metric is. And the mathematical formulation is very simple. It follows from analysis of variance. This formula is just to check the account of a change of climate change and their sample variance. And the first thing I did compare that relative agreement at local scale, at grid works scale over the whole world. So this is I'm showing for temperature. This is 30 initial condition done. The metric computed from 30 initial condition done. And this metric computed from the 30 models. This value is from 0.9 to running to 1.0. And if you see over most of the world, we have high agreement coming from both initial conditions and multi-model. This is for the temperature, and this is for the near term 2010 to 2039. When I look at precipitation, I should have changed the scale, but I have kept the scale same. The color scheme is the same, but the scale is different. This runs from 0 to 1. And this is for the precipitation. Again, I want to highlight this is near term. These lighter shades of orange or the blue shows less agreement among the models, and the deeper shades shows high agreement. For precipitation, especially over oceans and over tropics and some parts of US and even some parts of over India, we don't have that much agreement, either coming from the initial conditions, either coming from multi-model. So that means we have very high uncertainty coming from both initial conditions and for the multi-model when it comes to simulate change, when it comes to project change in precipitation. And this was at the local scale. Just to study this problem at multiple scales, what I did a kernel smoothing, especially at each grid point or draw a circle of a fixed diameter, and then I took a weighted spatial average and replaced this old value with this new weighted spatial average value. And I did this for precipitation just to see how this metric compares with the scaling, with the horizontal scaling. So this is what happens. This is how the smoothing works. So this is at the local scale. When I draw a circle of 120, this big circle on then 2500 kilometers, because of the smoothing, what is happening? This gray line is showing almost no rainfall. This deep blue is showing you have highest amount of rainfall. With this smoothing, what is happening? You have less and less gray area. And I increase this scale up to the hemispheral level and also to the global level. So what is happening because of this smoothing is that from the local scale where you see lots of gray and lots of deep area, blue area, you almost see whole world becoming almost raining. So when I compare the relative agreement for temperature and both precipitation, but first for temperature, here I'm showing this the horizontal scale, the radius of the diameter that I consider, going all the way from the local to the global scale. The dotted line is showing for the multi-model, the solid line for the multiple initial conditions, and here I have considered both summer and winter and also annual climatology. What I see here for temperature is that again these values are very high, and as you increase the kernel as you increase the horizontal scale, the relative agreement increases to the point for multiple initial conditions. This is higher than the multimodal and almost reaches 1. And this is, I'm talking about the near term. When I look for precipitation, I see different picture. For precipitation, this value is starting from for the multimodal. The dotted line is the multimodal. This is going from 0.2 to 0.4. For multiple initial conditions, goes from 0.45 to around 0.65. This is at the local scale, but as I increase the scale, this again reaches towards 1. So for the problem of interest, which is local to regional, I am operating at maybe at from this scale up to 25 kilometers. Here, for rainfall, internal variability is a dominant factor. So if any climate interpretation problem, we need to include the climate simulations coming because of different initial conditions. And this I also compare it at the mid-century and mid-century, and what I see here is that when I talk about the after 2050 or towards the 2100, then internal variability even for precipitation is not that much of a dominating factor. This again I did a simple comparison like the IPCC did, again plotted anomaly time series for changing temperature. I have used the same color scheme, kept the orange line for the internal variability and the blue line for the multimodal variability, and considered 3 different scales, global, land, United States and New York. In the actual paper, I have taken many more scale just to convey the points. I have considered US and New York. These blue lines, each of these blue lines is showing one of the model runs, and each of these orange line is showing one of the initial condition runs. The initial conditions runs are so close that they stick together and look like they are just only one line, but actually this is 30 lines that I am showing. What I want to convey from here that for temperature, our understanding has increased significantly, whether we talk about the global temperature or at a city scale. But when we go for precipitation here, and this is summer precipitation I am showing, our understanding at the global scale may be better, but when you talk about the US and when you talk about the New York at a city scale, we see lots of spread both in multimodal bonds or multimodal variability and internal internal variability. And again, this is a single plot that I did IPCC had done, where I'm looking at the relative contributions of uncertainty coming from multimodal and internal variability at different time horizons at multiple scales, going all the way from global land plus ocean to global land, then going to Northern Hemisphere, North America, United States, and 4 cities in over North America. And this is for temperature. What I see here is that multimodal bonds for temperature, as you go future in time, it dominates. Internal variability is not the dominant factor. But when I look for precipitation, that's not the case. For precipitation, internal variability is as dominant or as much contributing to the uncertainty as model response. And this was not reported earlier. The earlier literature has reported that there was published in 2011 in Climate Dynamics that model uncertainty is the one which dominates for projections in climate, projections of precipitations. Internal variability is not a dominant contributor. But their analysis was based on, again, very simple assumptions that they pick a regression line for several polynomial and then computed internal variability as the noise. But if we took the actual climate projections data, then that is not the case. This highlights further that any impact assessment that we do, where precipitation is the stress or a driver, we need to be considering internal variability into the impact assessment. This is the last figure that I have from this paper, where I'm showing the spatial maps of relative contributions of internal variability over 4 decades. This is this decade, this is the 3rd decade, and this is mid-century and then end of the century. This scale shows the orange line, the shades of orange line is showing the internal variability is dominating, and shades of blue line shows model variability is dominating. For rainfall, especially in these 2 decades, now in 3rd decade, over Northern Hemisphere, especially at the higher latitude, internal variability is the one which is dominating. But over tropics, the blue line shows that the model variability is dominating, which is again understandable because we do not understand that the rainfall, the mechanism for rainfall in these regions that well, and that's not implemented in the climate model. But again, for temperature, internal variability is not the dominant contributor there. All the analysis that I did here to characterize internal variability was based on the climate projections. In CIMIC high, again there are issues with that analysis. I will come to in the next slide. In CIMIC 5, recently, climate community has also trying to address this to characterize this internal variability by running decadal prediction runs. When I say decadal prediction runs, basically here they initialize the climate models with the observed climate system. They don't initialize with any hypothetical random way. This was a new effort that started in CIMIC 5. This is still in infancy stage. This is not right now. It's not the decadal predictions coming from these runs are not credible enough to characterize internal variability. Some of the issues that we have with these runs are that 70% of the world is covered by oceans. We have very poor observational record over oceans. We don't have uniform observations. The observational record is very sparse. And below subsurface, over oceans, we don't have that well observations record. And also, there are many ways to initialize these models, and there was no consensus built at that time when these experiments were run. So, modeling groups were left with their own judgment of how they will initialize these models. So, right now, this CIMIC 5 decadal predictions run is not in a stage where we can use these runs to characterize internal variability. However, going forward, we can see the potential here. So one of the major caveats of this work was that characterizing internal variability and characterizing multimodal variability from CIMIC 5 runs. So unlike say the 30 initial conditions which had been done with one model and 30 different initial conditions, in CIMIC 5 model, 30 CIMIC 5 models, these models have been initialized very different. All the initialization schemes across these models are different. Some of the modeling groups have given output of climate model outputs from 2-3 models. Maybe they might have used the same initial conditions, but different modeling group use different initial conditions. So essentially, when I'm characterizing multimodal variability from CIMIC 5 runs, those multimodal variability is also containing some information about internal variability. So that's one of the caveats that I have to consider in this analysis. But if you compare this analysis with the previous or the state of the art that is in the IPCC report, last year report, last year report, that makes even much bigger assumptions. So one of the implications of this work is that wherever we see internal variability as the dominant sources of uncertainty, we have to be using flexible design principle. We will not be using design principle based on likelihood, where we can using a Gaussian term and then we can estimate a 95% confidence interval. Wherever internal variability is a dominant contributor, we have to be more flexible in design principle because each of these future trajectories is a possible climate and we need to be considering all of them. Wherever we found that model variability is the dominant contributor of climate uncertainty, we need to improve our models much better in those places, especially in tropics over India, Indian monsoon we don't understand. So one of the broader impact of this work, as I keep mentioning, in the current literature or the current practice in climate adaptation is to consider many climate models with the impact assessment. As far as we concerned, when I look at the literature, I did not find a literature where people have considered multiple initial conditions and also in the climate impact assessment. So this was one problem based on the RFI work extension where we considered climate projections from all initial conditions, all models, all greenhouse gas emission scenarios in the CIMIC 5, almost 330 samples we considered here. What we are looking here is that we are looking at our production at risk over US in 2030 from all possible combinations of climate features that is available in CIMIC 5 over. And here we have considered joint dependence between water scarcity and warmer water. Anyone can cause a stressor for the power production. If you have no water available, definitely you cannot run the power plant. If you have water available but the water is warmer, then it cannot be used. So this was a broader impact of my work where here I'm showing a spatial map of risk profile, how which regions of the US will be water stressed, and these dots are showing the location of the power plant with the capacity, and this is a regional variation of how much power production will be at risk. Plants in southeast and south and north will be under most stress. And these are my journal publications. And with that, I would like to conclude my presentation.
Before we open up for questions, I have a couple of things. First of all, will you tell your committee in about 30 seconds what your next steps are?
My next step, I will be joining Tokyo Marine, where I was working as a Swiss Re as a NADCAT analyst. Here my role was more of supporting the underwriters, but here I will be taking additional role of doing research on climate change, especially hurricanes and floods. And also my next step is to continue my research on climate predictability and climate change, looking more on the care side.
Okay, so there is a concern in your committee, as you know, that your dissertation defense precedes your actual dissertation, right? Which is, I've never had this situation before. We have this now for logistical, understandable reasons, which is okay. But you need to make a clearer case about how everything is related and coherent. If you have a dissertation is clearly made there. Take about a minute to think about this. I can see sort of something emerging. There are some initial work which was useful, important, which led to your overall work. There's a motivation for your overall work. There's the main focus of your hypothesis-driven research, and there's a broader impact. Is there? Can you coherently take maybe half a minute or a minute, if you will, to think about this, and then coherently within 2 minutes express this, how these things are linked together as opposed to being just a collection of things?
So, as I mentioned in the beginning, when I was defining my research problem, I had some prior experience as a risk engineer, risk analyst. Especially, I was not engaged in more research activities. I was primarily supporting underwriters. And with this research exposure that I got over 4 years, where I learned about climate change, and especially in the work I did recently, where I was looking at climate change over next to 30 years, now to 30 years. With this much learning that I have, I will go back to the industry and I will try to incorporate this information into the risk model.
No, question is different. So you sort of get the picture that after this PhD, hopefully you'll be able to contribute to best practices in the industry. That's what you're saying. Learn where the best practice was. That has been evolving. What you learned here with that. Question is, you presented 5 papers, mainly, and you showed some others, like 48%. How are these connected into one coherent picture that will define your PhD dissertation? How are these connected? The work itself, not what you learned.
Okay. So I started with model evaluations, looking at this climate corrections towards the end of the century. I first looked at mean and signal climatology of rainfall, and then I moved to wind extremes. And then I moved to evaluating to improve the understanding of climate internal variability and multimodal variability from now to 30 years. All my work has been to somehow climate projections from now to 30 years, even end of the century. So my work is to understanding the multimodal variability and internal variability in climate projections and a set of our climate models.
Okay, so we'll talk more about this, but meanwhile, any questions from the audience who is not a member of the committee?
So I was curious. So you said 31 full, so 30 different models of orange, right? And then you have one. Then you have on the other side you look at 30 additional conditions in one model. Talked a lot about the, which I think is important. Talked about the total variance and break down the fractional variance. They're both, but trying to put my stakeholder hat on. Regardless of where that variance is coming from, if I look at one of those, so if I look at one set of 30 versus the other, does it give me a different upper bound on something like precipitation? Does it give me a different upper bound? Is that something that you look at? Lower bound, right? Upper or lower bound? You have different amounts of variance. So what are the actual answer in terms of those sets? How different are those two sets of simulations in terms of giving you an answer, especially over that short like scale of time, right? Because as a stakeholder, I might not, if I'm getting an answer that's roughly the same, regardless of whether I got it from 30 different climate models, 30 different conditions, I don't necessarily care. I just
Yeah, so let me see if I answer this question. So if I look for this figure for US or maybe for New York, if this upper bound is somehow also coming from internal variability, maybe not from the model variability. So if you just consider the multimodals, then you may not be getting some of these. Yeah, orange is internal and blue is multimodal.
Okay, but is it also true that you don't care? So
no, I care. The other reason is that the treatment is different. So the way I would take a multimodal variability into design consideration for risk consideration very differently than I consider for the multimodal for the internal variability.
So say I'm a stakeholder and I just want to know. So what's the worst and better case? What's the upper and lower bound for my question was more like, did you observe doing this research that that answer was different because this set of 30 versus this set of 30, right?
Yeah.
Without caring about how the variability works and stakeholder, I don't understand all this stuff. But upper and lower bound, are they different if you take 30 different models versus 30?
For precipitation, it would be different.
Temperature.
For temperature, if you see these pictures logically, each internal is contained within one model. But also there is a caveat here. Here I am characterizing internal variability coming only from one model. If I look at conditions from different models, we are not sure if this may exceed also. So the one green line that you see here is the same model that is part of the CINIS 5 model. Just because this is just I want to show that because this particular maybe model giving a little more higher or maybe lower. So if I take another model, maybe NASA model or some Japanese model, then 13 cell conditions, this could go out of one also. We don't know the answer.
This is one valid stakeholder question, which is the bounds themselves. Can you explain also the connection with what Paul Gershon talks when he talks about flexible design? Would you like to say, just explain?
Yeah, so flexible design is that we do not know, especially in case of rainfall, whether there will be dry future tomorrow or wet future. But if we have, if we want to prepare, we need to prepare for both. The way it works is that we may be building, just to give an example, again coming from the Paul question, so when he talks about the building sea wall to protect from the sea level rise, if we are not sure about how much sea level will be rising, then we can build a foundation for the worst case sea level rise. But we will not build the height of the wall that much. But in case 10 years, 20 or 30 years down the line, if for sure the sea level is rising furthermore, then we have the foundations already built on which we can increase the length of the wall.
And how would that change if, let's say, initial management was? How would this principle change? The initial intrinsic management was?
If there is no intrinsic value, then I would consider reducing mostly only from multimodal variability. There would be again if the multimodal variability is again giving these kinds of bonds, there I can consider some kinds of distribution coming from a dispersed model, and then you can estimate a range of confidence interval, and then I will work with that confidence interval. However, I cannot do the same with this internal variable.
And my basic takeaway here is that we're pretty good at the global scale saying what change we're heading towards by these various models. And that's probably very helpful for folks like Alan in Paris to figure out what we should do something. But we're really challenged when we get down to a much more localized perspective. Somebody has to make decisions about what to invest in making a certain level of change. And I get that we just laid out here that tends to give them some variability in design to support that. But forecasting out maybe 5 years, if you had limited resources and you didn't have to go work for a living, where might you be with this problem set of being able to downscale this predictive models to a point where it can usefully inform somebody who's making a decision about a seawall, about how high they should locate a substation, any of those sort of mundane issues sort of apply. So, given your work today, where do you think you could advertise yourself if you had unlimited funding and all the time you want?
Again, just to, since whether you are doing a thought question, let me do a thought experiment. So, suppose I have unlimited funding, even after 5 years I become super god. And I can resolve all the models. I can understand everything about the climate processes, and I can incorporate in a numerical model. Computation is not a problem for me. But still, climate system, as I said, is chaotic. There will be uncertainty. Just to give an example, just to think very simple example. If I take a pen and write my name twice, and if you match pixel by pixel, there will be some differences to the same guy writing the name immediately at the same time. But you can read that. So what I want to say is that there is internal variability, the chaotic component of the system, which will sometimes go up or down. Which variability are run at an interannual scale, decadal scale, multi-decadal scale. And we don't know whether this multi-decadal scale variability is going up, sometimes going down where it is, when it will come. So even if we become perfect with the models, we have to be still prepared for the internal variability. And especially only if we are talking about now to 20 or 30 years. If you go further in the future, this variability will not be there. Only the climatic trend will be.
May I suggest again that you give a good answer to a question which he did not ask. It was a good answer. Question was more on downstream. So yes, this is not completely yes to your work directly.
Actually, there were multiple questions. I remember the latest question. The first question, yeah, the down scale. Yeah, you said this is working good at the global scale, maybe only for temperature, for rainfall, but still maybe not that good for at the global scale. And also, when you look at the global scale, if you just compare the whole rainfall, maybe matching, but how about the spatial variability? Maybe model is simulating more rainfall at one place, less rainfall at another place. Maybe total may be right. So even at the global scale, when it comes to spatial pattern, hydrological balancing, cycle balancing, which is still not well captured in this model. But when it comes to the regional scale, the northeast, the situation is even more starting. At local scale, we don't even trust that.
So what does that mean for downstream?
So in next 5 years, I'm not hopeful that these climate models will improve to the point where these will give very credible projections at regional scale.
So hence, is downscaling needed or is it needed?
Downscaling is definitely needed.
And what do you see will happen in 5 years? That was in the state of the art of downscaling.
Again, your access uses.
Yeah, so I'm saying unlimited, somehow unlimited. Somehow unlimited. Yeah, let all people let work unless until we understand the atmospheric processes well, how it is there. If we maybe again just reducing this grid, the distance between two grid points and developing different parameters of things, I don't know whether it's going to solve the problem. If we can understand everything well about these processes and can implement the climate models, then we can do it. But 5 years will not be the sufficient time. Even we involve too many human resources, just have all the supercomputing power. Because some of those I'm assuming that those concepts don't exist, but the moment you reduce the grid size, the requirement of computing power is increased exponentially, and the kind of computing technology that we have not even sufficient to run those in time.
Okay, so we talk about this. This is an important philosophical question, which is not quite directly related to what you did, but we can talk about what is happening. But please ask one if anybody remotely has any quick question.
Anybody has any questions for me? Yeah.
All right, remote audience. Any quick questions for Devashish? All right, thank you. Karsten, please stay on the line. And here, if you are in the committee, please stay here. Otherwise, please, Devashish will be drilled now. So please let him speak.
Hi, Rup. Devashish, this is Karsten.
Yeah.
If I'm the only remote participant, I can also call you directly or vice versa if that's easier.
Means you you want to call me on a Skype or on the phone?
Either way. Maybe on the phone is easier.
Do you want to note down the lab phone number you can call, and I can put them on the speaker phone?
Yeah, that might be easier. Then we don't have to keep the WebEx open. Sometimes there's a little echo.
Okay, so the phone number is 617
617
373
uh-huh
6005.
Okay, I'll call there right now.
Yeah.
He is on okay. We heard it on so around this it's a great opportunity. Basically,
Yes, I can hear you.
our center support under some excellence in which we could towards innovations that we embrace. So 3 years time, first year's assessment, 2 years of innovations that can be adopted.
Laura? Hello? Laura?
Good job.
Let's see.
Yeah, he hasn't put them in black before yet. So.
Oh, okay.